Hi, welcome to online lecture series on audio and speech signal processing. This is lecture 6 and in this lecture we will talk about how to find the short-term zero crossing rate of the frames of the speech signal in MATLAB. As we discussed in previous video, in order to process the entire speech signal, we divide the entire speech into small frames, and whatever operation we perform on these small frames, those are known as the short time or frequency domain processing. So if we are doing some processing on a frames in time domain, then that will termed as short-term time domain processing. And if we are doing some frequency kind of processing like frequency response or Fourier transform on those frames, then that known as short-term frequency domain processing. So these are quite important, and obviously all this involves the framing part. So in this video, in last video we also talked about how to remove silence and what is voiced and voice signal and what is silence, and removing silence is a critical portion or critical part in speech signal processing. So in this video we'll talk about another method of removing the silence from speech, and that is more accurate than that of the amplitude based method. This is the based on zero crossing rate. So it has been observed like zero crossing rate of a voiced speech and of the noise is different. So when we are speaking and we take the zero crossing rate of the voiced portion, that will be lower, and for the noise it will be higher. So based on this method, based on this significant information, we can remove the silence from the speech signal. So we will learn how to do that in MATLAB and how to simulate it. Again, you can also find the theoretical part of all of this entire video on our website, that is www.ZCR. You can also download the MATLAB code from that website. So open MATLAB. First in MATLAB, again we need to let's go to the folder where videos are lying. Now close all and now first let's read the audio file. So we are reading audio file by the command audio read, and let's plot this one. So this is our audio file which contains some speech portion, some of the noise portions or the silence portion, which we are intending to remove from it. So prior to do any processing, let's do some normalization part of it, divided by maximum, absolute of maximum, that's done. So let's see how this looks like. So maximum amplitude is 1. Now it's everything is fine. So what we did, we max and then absolute. Okay, doesn't matter, it's done already. CLC. Now we will convert this entire speech into small frames. So we have discussed the method of doing this in previous video. We also have created a short program of framing which returns which takes input of the entire speech signal and returns the frame out of it. So let's call this one and let's framing, and then the data part, and then fs sampling frequency, and then f underscore d is the duration. So we are taking 25 millisecond of duration. So and let's also define the duration of the frames, that is 0.025, or we might need it. So it has converted the entire speech in frames, and we are getting total 300 of the frames, and each frame length is 1103 numbers of samples. Now there are several ways to do the framing, and out of which several ways we will find one by one. And prior to do that, let's take an example. Prior to applying all those algorithms on the frames, let's take an example and understand how it is happening. So we have a this vector x, and it contains, suppose, this information. So zero crossing will be whenever the sign is changing from plus to minus 1, that will be termed as the zero crossing. So 2 to minus 3, 1 zero crossing, minus 3 to 4 second, then plus 5 to minus 5 third, minus 6 to plus 2 fourth, then 2 to minus 6 5, and then minus 6 to 2 6. So there are total 6 zero crossings. So one of the way is to one of the simplest algorithm to detect the number of zero crossing is simply by go, if the current sample is positive and the next sample is negative, then there is a zero crossing. So update the value of zero crossing again, and the same if the current value is negative and the next value is positive, again there is a further zero crossing. So based on this simple term, we can we can derive the algorithm simply. So let's say I goes from 1 to 0, and prior to it we define zero crossing 1 based on first method as 0, and let's say we are going from I equals to 1 to entire length of x minus 1, because we will be needing I plus 1, because we want to compare with the next sample. So now if we go for if x of current sample is greater than 0, right, and make it in and next sample is less than 0, then there is a zero crossing of then ZCR1 equals to ZCR1 plus 1. Else if current sample is less than 0 and next sample is greater than 0, then again ZCR1 is equals to plus 1, and then so ZCR1 is simply 6. That's it. This is exactly what we predicted. There is a 6 times when this waveform is crossing the 0 line. So this is the one simplest way. Another method is if we look this this particular method we just discussed, that is a little time consuming as far as the processing is concerned. So we can do another short way, like if we find the number of like how many values are greater than 0. So we will get, like if we take y equals to x greater than 0, and we'll get this one. And now if we take the difference of it, then difference of it will be minus 1 1 minus 1 1 1. And so now just have a look if okay, we do it again. Now if we just add all these numbers, then it will be equals to the zero crossing. So simply we can write it like sum of absolute value of difference of x greater than 0 will get exactly the same thing, that is zero crossing rate. So ZCR2 we can write it like this is the very simplest way of calculating a zero crossing rate of actually these are the number of zero crossing. For making it a rate we need to divide by the total number of samples. So first we are discussing the number of zero crossings. So this is the simplest way to find the zero crossing of any vector, and it's simply 6. That also cool. So there's another way as well, and that is based on the standard definition of the calculating zero crossings. That is, if we cross multiply or if we multiply current vector, suppose current vector is a length of 6, so if we multiply starting 5 element with the remaining next 5 elements and sum them together, again we will get the zero crossing rates. So let's see what I am saying. So if we multiply 1 2 and minus 1 with x of 2 2 and, so these are starting less than 1 series, this is remaining less than 1 series, and so we'll get this. And now if we find number of values which are greater than or less than or equals to 0, we'll get this, and if we simply sum them together, again we will get zero crossing rate. So this is another simplest way of finding these zero crossings, equals to sum of x of 1 2 and minus 1 multiply with remaining length, remaining vector, and then find which are less than 0, we'll get the same zero crossing rate of the 6. So these are the popular very easy 3 different methods of finding the zero crossing rate of any vector. Now we will extend this complete algorithm of these 3 to the frames. So we can employ any of the value, or prior to doing it, let's take as in the starting of the video we talked about there will be different zero crossing rate for voiced samples and unvoiced samples. So as we last time discussed, frames 110 frame contains the speech portion. So let's take speech portion and let's plot it first of x, and as we discussed, it is like a sinusoid, a repeating waveform. So this is clearly a speech signal, and let's try to find the zero crossing rate of this one, and we'll go with this method. So like this ZCR3 now is 15, so for speech portion zero crossing rate is 15. Now let's say we have frames of 40th length, frame number 40, and again let's find the zero crossing rate of it. So it is 76. So there is a wide difference between voiced zero crossing rate and the non-voiced zero crossing rate. So this difference can be used further to identify how to differentiate between voiced and unvoiced or noise sample, and based on that we can also remove the noise from the speech. So now let's further move further, and now we will extend this algorithm to remove the zero crossing to find the zero crossings of entire frames. So now first because we want to do on entire frame, so first we need to know how many rows are there. So R and C will contain rows and columns. This size command is there which converts into rows and column, and then for I equals to 1 to number of rows and for each row we take it in frames, frames of I, and then we go for the zero crossing rate of this one and we make it I, and we are using the third method for that. Let's see if everything goes fine. Yeah, so we have a vector of ZCR3 which is simply the zero crossing rate, and if we plot it, so these are the zero crossing rate of different frames. So there are 325 frames, so 345 frames, so these are 345 different samples. So this is the simplest, this is how we can find easily the zero crossing rates of various values, various samples. Now we can remove based on some threshold, like which have the higher zero crossing rate, we can remove all those frames from our speech signal, and then we can move further for doing some other signal processing technique. So now if we want to calculate, because these were the zero crossing rate, if we want to calculate rate, so that will be simply divided by length of x. So we'll get the rate value. So now it will be in the range of we can also make it in the range of 0 to 1, so that it becomes easy for us to identify. So now if we plot R, it will be between 0 to 1. Now let's have a comparison view between these two things, between input signal and the corresponding wave. So that is what we have written a small code for that here, like plotting both the waveforms at the same time. So let's run it, and this is the waveform where this blue curve or blue graph shows the original speech waveform, and this red graph shows the corresponding zero crossing rate. So it is a kind, what we have done, because the length of the frame was 1103 and zero crossing rate is single value, so we have reconstruct the entire wave of the same length as that of the original signal, while repeating the current value of zero crossing up to the frame size. That means for frame 1 we were having zero crossing rate, suppose x, so that has been repeated up to 1103 samples. So that was the simplest algorithm we found, and you can get it from the code. This is the way we have done it. This is the way we have done it from this one, and for plotting we have used this one. So this is on the way. So if you will look carefully, the silence portions have higher zero crossing rates, and which are speech, those have lower zero crossing rates. Same all over the line, or even up to this one, this has higher zero crossing rate. So when we removed silence based on the amplitude portion, this is the noise part only, and this was also coming into the picture because the amplitude is higher. But in the zero crossing rate, if we make a threshold of some this value, say 0.2, then we can easily neglect this portion, as this contains no information as far as the speech is concerned. So now we will go for removing the silence from the speech, and that is very easy. We have all the rates there, so we will just simply find all those values or for rate which have less than 0.2, because for the voiced portion this rate will be less, and for the non-voiced portion the rate will be higher. So we have simply used this command and we'll get all the IDs, and we will get all the frames without silence simple by frames, and only select those frames which have zero crossing rate less than 0.2. Simple. And now we can reconstruct our waveform again simply by reshape, as we discussed in previous video. And now we can plot both the figures like original. Let's say plot original signal, that was data, and then hold on command and then plot new waveform, that is data underscore reconstruct, and let's put in different color, and red, let's say in green. So let's see what is plot data underscore r. Okay, data underscore r doesn't contain any value. Reshape of RWS. Okay, R contained on 345, so we have done something wrong. So we need to go back previous commands of calculating R. So R was calculated by this. So we are getting only one value. Okay, all our variables have been lost because we run this script. So we'll use this value, this contains the same, this is ZCR1. So we'll use this one. This is the same as done by previously, but only the thing is our previous all variables have been lost, so you can continue with the previous one, that will be same, and then reconstruct the signal. Yes, so this is the green portion showing the reconstructed signal after removing silence from the speech. So as we talked about, these small portions have been removed completely in the reconstructed wave, and as this contained no information, even we can let's say hear the sound. So this is how we can remove this particular silence from the speech. And this is also not very much used way in for speech processing, because in speech processing there are several factors which are involved into it. So this is one of the way to use to remove silence from the speech. Now in next video we will talk about short time energy or short term energy based silence removal from a speech. So I hope you understand how to calculate zero crossing rate and how to remove silence based on zero crossing rate in MATLAB. So that's it for this video. Thank you.